Hi, folks. In this section, we're going to learn about special systems of linear inequalities. Up to this point, every system of inequalities that we've looked at has had one solution. We've had lines that have intersected at one point, and we're going to look at a couple of different cases today. One where there's no solution. Having no solution occurs when lines are parallel, so those lines never intersect. Um, this can sometimes be identified graphically. It kind of depends on how zoomed in or out you are, because lines can sometimes appear parallel if you're zoomed in, but not actually be parallel if you're zoomed out. The best way to tell if two lines are parallel is to see if they have the same slope, but with different y-intercepts. The other scenario you can have with systems of equations is you can have infinitely many solutions if um, you have two lines that are exactly the same. So it might look like you have two different equations, perhaps because they're written in different forms. But in reality, when you rearrange them, you find out that you have the same equation written twice. So the two lines actually overlap everywhere. And in that scenario, you have infinitely many solutions. And that happens when you have the same slope and the same y-intercept. So the line is actually the same. So let's look at how we can identify these examples. Um, and sometimes the identification is obvious if you're paying attention, but I also like to show students how it appears with elimination or substitution, because sometimes if you're in a testing situation or something like that, you are just kind of in a groove and you don't see kind of the big picture. You don't notice that two slopes are the same, and you've already done elimination or substitution. So I want you to see what that looks like as well. So if I look at this system of equations here, I can tell from that format that these both have the same slope and different y-intercepts. But again, as I said, I want to show you what this looks like if we say do substitution. So let's do this, substitution. I'm going to take this value of y and substitute it in where I have y written on the second equation. So I'm going to rewrite this as 2x plus 1 equals 2x minus 5. So if I solve for x, I need to get all my x's on one side of the equation. So I'll subtract 2x from both sides. And I end up with 1 equals negative 5. This is a false statement. 1 does not equal negative 5. And therefore, this is an indication that my equation has no solution. No solution. Um, Now, something similar would have happened if I had done elimination as my root here. If I just subtracted this second equation from the first equation, y minus y is 0, 2x minus 2x is 0, and 1 minus a negative 5 is like 1 plus 5, which is positive 6. And clearly 0 does not equal 6. This is false. So once again, I find a situation where there is no possible solution, no solution, and the only reason that this no solution can come about in a system of equations is if you have parallel lines. So let's look at another example. Solve this system of equations. In this case, I could do substitution again by, let's see, to get y all by itself, I should add 2x to both sides of the equation. So I would have y equals 3 plus 2x. So then I can take this y value and plug it in for y here in this second equation. So I'll have negative 4x plus 2 times that 3 plus 2x equals 6. And now x is the only variable I have in this equation, so I'm going to simplify and solve for x. I'm going to do the distributive property here. Negative 4x plus 6 plus 4x equals 6. Let's see, I'm going to combine my like terms. Negative 4x plus 4x is 0x plus 6 equals 6. This is a true statement. This is always true. It's not helpful. It doesn't tell me what x is. It doesn't tell me what y is. But it is helpful in the sense that because it's an always true statement, then this means that there are infinite solutions to my system of equations. Infinite solutions. And this happens because my equations are actually for the exact same line. Same line. So let's see how we could demonstrate this in a different way. Let me just erase some of my extra writing here so that it's clearer to see what we're doing here as we use elimination as our method of solving these equations. Here I can see that if I multiply the top equation times 2, I can have matching coefficients for my x. So I'm going to multiply by 2, and that's going to give me negative 4x for my x variable, or my x term, positive 2y for my y term, and 3 times 2 is 6. Now, by doing elimination, it's actually more obvious here that my two equations are, in fact, identical. But again, if you're in the thick of things, maybe you don't notice that right away, that you have two of the exact same line. But I'm going to subtract these terms because negative 4, that coefficient for the x term, is exactly the same as here, negative 4. Then I do subtraction to actually eliminate the x. And when I do negative 4x plus a positive 4x, that's 0. 2y plus a negative 2y is 0. And 6 minus 6 is 0. So once again, I have a true statement, a statement that's always true. And again, that means I have infinite solutions. I have two equations that express the exact same line. So whether you are graphing and can visualize whether there's one solution, no solutions, or infinitely many solutions, or whether you're dealing with equations, you can use substitution or elimination to determine if you have no solution or if you have infinite solutions, as in this second example. So let's look at a real world scenario where this might come up. Okay, you buy one bag of dog food and 2 bags of treats online for a total of $48. A few weeks later, you buy 2 bags of the same dog food and 4 bags of the same treats for a total of $96. Find the price of each bag of food and each bag of treats. All right, so I want to know the price for the food and for treats. And so I'm going to go ahead and call the price for the dog food X, and the price for the treats, I'll call that Y. And this is one of those scenarios where we have two items, each with their own rate. In this case, each with their own price per item. And so standard form is going to work well in this situation. So I'm going to do the number of bags of food, 1 bag of dog food with a price of X, plus 2 bags of treats times the price of treats, which is Y, equals that total of $48. Next, I'm going to write an equation to express that second shopping purchase where I bought 2 bags of dog food and 4 bags of treats for a total of $96. With these numbers, with this kind of layout of equation, it looks like elimination is best for solving this. What I'm going to do is take this top equation and rewrite it. I'm going to multiply it by 2 so that my x coefficients line up with each other. I'm going to write 2x plus 4y equals 96. Now, because my coefficients match each other, I'm going to go ahead and subtract the purple equation from the red equation, the second red equation. And 2x minus 2x is 0. 4y minus 4y is 0. And 96 minus 96 is 0. Here, I have a statement that is always true. 0 equals 0. Always true. And so, therefore, I have infinite solutions. Infinite solutions. We've done problems like this in previous sections of Chapter 5, and we were able to find solutions for those problems where we did two different shopping trips. The problem with this shopping trip is that my purchases during the second shopping trip were an exact multiple of a previous shopping trip. So my equation didn't turn out to be any different. If I'd bought a different proportion of dog food to dog treats, we would have been able to deduce the prices of the individual items. But in this case, the shopping trips were multiples of each other, and therefore the equations were the same, and we have infinite solutions. I hope this helped.